Hi, welcome back to Principles of Communications. And in this video, we are going to solve practice problems regarding receivers. Okay. Number one, it states that a tuned radio frequency receiver is to be designed with a single tuned circuit using a 20 microhenry inductor. First, we are asked to calculate the capacitance range of the variable capacitor required to tune from 535 to 1605 kilohertz. Okay. First, we write the given. We have an inductance given that is L equals 20 microhenry. Okay. And we have our frequencies here, our frequency range 535 kilohertz and 1605 kilohertz. Now, recall that for a resonant circuit, the resonant frequency is equal to 1 over 2 pi squared of LC. And if you square both sides, square, you can see that it will become f squared and it will become 4 pi squared, and the radical here will cancel out. And if you solve for c, you're gonna end up with this equation: c equals 1 over 4 pi squared f squared times L, or the inductance. And then we just substitute our values: 1 over 4 pi squared times 535 kilohertz. That's it. That's our lower frequency range, and that will be squared times the inductance, which is 20 microhenry. And uh, what we get is the value of capacitance, which is equal to 4.425 nanofarads. Next, we have to compute for the upper frequency range. We do the same thing, and we use the same equation: c equals 4 pi squared f squared L. And we just substitute our values: 4 pi squared times 1605,000, which is because it is in kilohertz, and that will be squared. And then we substitute our value for inductance, that is 20 microhenry, and we come up with our capacitance, which is 491.65 picofarads. And then we write out our capacitance range, wherein our capacitance must be greater than or equal 491.655 picohenry, rather picofarads, and it should not exceed 4.425 nanofarads. For letter B, under the same question, we are asked to determine the Q, or the quality factor, given that the ideal 10 kHz bandwidth is to occur at 1000 kHz. Recall that the bandwidth is equal to frequency divided by the quality factor, and we basically cross multiply the bandwidth and the quality factor, and we end up with this equation. So the quality is equal to the frequency divided by bandwidth. We simply substitute our values. Frequency is equal to 1000 kilohertz. That's it. And then our bandwidth is 10,000 hertz. And dividing them, we get the answer, which is the quality factor is equal to 100. Letter C. We're asked to calculate the bandwidth of this receiver at 535 kilohertz and at 1605 kilohertz. We simply use the same equation as before. Bandwidth is equal to the ratio of the frequency to the quality factor. and that will be 535,000 hertz, which is our lower frequency range, divided by our quality factor, which is 100, and we end up with 5,350 hertz, or 5.35 kilohertz. And for the upper frequency range, we simply use the same equation: frequency divided by our quality factor, and that will be 1605 and 1000 hertz, because it is in kilohertz, divided by our quality factor, which is 100, and then we end up with 16,050 hertz, or 16.05 kilohertz. Number 2, it says that a receiver has a sensitivity of 0.75 microvolts and a blocking dynamic range of 80 decibels. What is the strongest signal that can be present along with a 0.75 microvolt signal without any blocking or desensitization taking place? First, we write the given. We have our sensitivity of 0.75 microvolts, and if you recall, sensitivity is the minimum voltage. So, we write our Vmin 0.75 microvolts, and the dynamic range is equal to 80 decibels. So, dr is equal to 80 dB. And let us recall our equation for dynamic range, which is equal to 20 times the logarithm of maximum voltage divided by our sensitivity, which is the minimum voltage. And we substitute our values. We replace the dynamic range by 80 decibels, and then our sensitivity by 0.75 microvolts. And if you want to solve for this, we simply divide both sides by 20 first. 80 divided by 20 is equal to logarithm of our Vmax divided by Vmin. Okay. And if you raise both sides by 10, remember the property of logarithm. This will cancel out, and we're left out with, and if we cross multiply our sensitivity or minimum voltage, we end up with Vmax is equal to our minimum voltage times 10 raised to 80 over 20. And that will be our final answer, 7.5 millivolts. Alright, thank you.